All right, we should start.
Okay, so here is the agenda for today. I hope I'll get 2 or 3 parts of it. Extend our study to periodically weighted thetas, then combine, well, eventually combine, for now just review and continue harmonic polynomials, saying a bit more about the structure, and finally talk about what I've always heard of as Murphy's Law, but I'm told across the pond is sometimes known as Todd's Law. Same thing. At any rate, okay, so, oh, we have no paper. Oh, here it is. Sorry. Lots of paper. Okay, so we started with theta functions of a lattice, either the capital or the lowercase theta. Let's just stick with lower cases for now. So we have a theta function of a lattice, and that's, I claim, to be a modular form if the lattice has rational inner products. I only showed it in the special case of an even unimodular lattice. And we generalized, or at least we outlined, a generalization to the case of theta function weighted by a harmonic polynomial p, of which we'll say more soon. And that's what we need to keep track of not just the length of vectors, which is what theta keeps track of, but also of their angular distribution. And there's another direction where you can generalize this, which is that you keep track of L together with some alpha, and alpha is periodic. And that is to say, it depends only on the coset modulo some sublattice. And these you need, well, there are 2 reasons you'd need them. One is perhaps you want to count instead of just representations by squares. So in the classical example that L is Z4, and we want to find vectors x1, x2, x3, x4 of a given large norm. But maybe we want to find 4 squares of numbers whose last digits are, I don't know, maybe 1729 to pick some random number. And of course you can't represent every number in that form because there's a congruence condition mod 10. So let's say try to represent just numbers n congruent to 15 mod 20 if I did the arithmetic correctly. And to count those, you need to to form a theta function for which you restrict the vectors to those in a certain congruence class modulo the lattice of integers, all of the integer quadruples divisible by 10. So in that case, you'd make alpha be the characteristic function of that coset. So if you're not so interested in these questions, you are unfortunately forced to deal with these kinds of lattices in any case, because essentially the only way to prove that the theta function of a general lattice is modular, as far as I know, is to extend your universe of discourse to theta functions weighted in this fashion, and then sort of deal with batches of them where you fix L and L naught and vary alpha. And once you have those, of course, you can imagine combining the 2 of them and look at theta series weighted by L and a product of some harmonic function and some periodic function. So this would be the function taking tau to the sum over all lattice vectors of alpha of v times p of v times the usual e to the pi I norm tau. And having said that, you of course know what, having heard that, you of course know what theta L alpha is. That's just the case where p equals 1. And these 2 you know already. So, things are not quite as bad as you might think from this picture, because we can, oh, you can't see the whole picture. Here we go. No, now you can't see the tau, but you know what's there. Okay, so one useful simplification is we have a lattice with rational norms and we have some sublattice, and we are going to look at functions on L that are periodic with respect to L naught. And in fact, we can extend this further to find some lattice M contained in L naught and some lattice whose dual contains L. And so that means if you're looking for the theta function of L naught periodic functions on L, you might as well be, as long as you can do M periodic functions on M star, that will include in a special case L naught periodic functions on L. And it turns out that it's this case which is easiest to deal with. And how do I know I can always do that? Well, I can let M be the intersection of L naught with L star, and that forces M in particular to be contained in L naught, and then that makes M star the span of L naught star with L, so in particular it contains L. And so I found my pair of lattices like this, and then that in particular makes M an integral lattice, because the norm of any vector is the inner product of that vector with itself, which being an M is also an M star. But as we have seen already, it's particularly convenient to be able to work with lattices for which all the norms are even. And well, you can either go further and look at only the vectors in M which are multiples of 2. Perhaps more convenient yet is to look at just the even sublattice, which is of index 1 or 2 of M, and then look at the orthogonal complement of M, excuse me, not the orthogonal complement, dual of M even, and then you're working in a situation where you have functions on the dual of an even lattice that are periodic with respect to the even lattice itself, and that's a situation to which we can most easily apply our Poisson techniques seen already. I'm not going to do this right now. I hope to have some time on the very last lecture to actually do this in full generality. For now, I'll just illustrate how it works in one or two, again, simple but important special cases. And so I'm going to consider the example where L is an even lattice with the property that L star, I mean, it will work if L is self-dual, but it's more general than that. All I need here is that a dual lattice becomes even if you double all of the norms. That is to say, L is an even lattice, and L star is a lattice all of whose vector norms are even, if all of whose vector norms are integers, but some of the inner products may be half integers. And these lattices show up not too unnaturally, so some classical examples are the D4 lattice and the Barnes-Wall lattice of rank 16, which will be our other paradigm here, which is also the laminated lattice lambda 16. And the punchline will be that to keep track of a transformation of the theta series of either one of these lattices, L and L star, well, L star doubled, under our basic generators of the modular group, you'll need to keep track of both of them together. So being even, we know already that both of these lattices have theta functions which are invariant under translation by 1. What happens if you try to look at our other generator, which is tau going to -1 over tau? Well, I'm not going to try to keep track anymore of the exact powers of t and I and 2 that show up, but we know already that this is some elementary factor, which is annoying to keep track of, times the theta of the dual lattice evaluated at tau. But the theta of the dual lattice is not what we are trying to keep track of. That's the theta of the dual lattice doubled evaluated at tau over 2. So now these numbers tau over 2 and minus 1 over tau have a product that's not 1 but a half, and so that means what I really should have done is look at theta L evaluate at minus 1 over 2 tau, and that would take me to the other lattice, theta L star 2 evaluated at tau. And likewise, because this is the map taking tau to minus 1 over 2 tau in involution, it follows that if I apply this transformation to the Theta series of the other lattice, I come back to the Theta series of the original one, evaluated at tau. So what that means in this case is that, okay, we have generators not of the full modular group, but of the group that I called gamma of 2 naught plus, that's generated by tau goes to tau plus 1, and tau goes to minus 1 over 2 tau. Remember, that's the one that has for its fundamental domain a hyperbolic triangle, but with the odd angle being pi over 4 instead of pi over 3. And so for this group, we end up finding that theta L and theta of the theta of the scaled dual lattice are both modular for gamma naught of 2 plus. You can hardly see this, but at least you can hear what I'm saying, I hope, thanks to this fancy clipped microphone. At any rate, so these are modular, but to prove that you have to keep track of 2 of them at once. Now, I haven't shown you any weighted ones yet, any periodically weighted ones yet, at least not obviously. What we'll see is that this one is basically a periodically weighted one because theta of L star of 2, that gives you, it's just one of the cosets of L star of 2 in L, L star of 2 in L, and, well, that wasn't quite right, erase that last sentence. Okay, so let's keep the situation that we were in before. So remember again, L is even, and L star scaled by 2 is even. And now I'm going to look at the theta series of L plus a dual vector. That is to say, fix some W star, fix some W star in the dual lattice. The dual lattice, because L is even, is particular integral, so the dual lattice contains L, and so L plus W star is some coset, and if I look at the theta function of L plus W star, what do I mean by that? That's equal to, of course, it's the generating function that keeps track of all the norms of vectors in that coset. E to the power pi I v tau, except this time only staying within this coset, and that's an E. Sorry about that. That's a special case, of course, of a periodically weighted theta function where I'm looking at all vectors in L star, but I'm multiplying the usual factor by hidden alpha here that is 1 if you happen to be in this coset of L and 0 otherwise. Okay, so what does that look like? Okay, first of all, what happens under tau goes to tau plus 1? Well, we know already that to do that, we need to keep track of what this inner product is modulo 2. And fortunately, all of these inner products modulo 2 are the same, because if I take my vector v and shift by, okay, so I have my vector v in L plus W star, and I shift by some, how do I do this? Oh, here I go. So any vector in here is v plus W star, so what is the norm of that? Well, it's this number, which is a constant. It's the norm of my coset representative. And that norm, remember, is an integer, possibly not even, plus twice the inner product of V with W star. VW star is an integer because W star is a dual vector. So this whole thing is in 2z, plus, of course, the norm of V itself, which is again in 2z. So that means that all of these vectors here are either all of integer norm or all of half integer norm. In the first case, I get that the theta function at tau plus 1 equals the theta function at tau. In the other case, it's multiplied by minus 1. So it has a simple transformation rule. In particular, of course, if I translate tau by 2, then I get the same thing. The interesting question is what happens when you apply our usual Poisson summation to find what happens as you take tau goes to minus 1 over tau. And the nice thing that happens there, if you look at the proof of Poisson summation, you take your general function on Rn, you form a new function that's periodic by summing all of its lattice translates, find the Fourier series of that function, and then evaluate at 0 to get on the other, and evaluate at 0, evaluate the Fourier series, that gives you this Poisson summation formula. What we're doing here is the same thing, except instead of evaluating at 0, we're evaluating at W star. So what happens there is that we find that, again, I'm going to suppress those annoying factors of t and I and so forth. I'm just going to get the sum over all dual vectors of the usual thing in the Theta series, e to the pi I v star tau, but multiplied by a twiddle factor e to the power 2 pi I times v star inner product of v star with w star. And again, this is a half integer because if I scaled L star by 2, I'd get an integral lattice. And once more, that's a half integer that depends only on what v star is mod L. So that means that we started from one of our theta functions that was theta functions that was weight of L star weighted by some L periodic function, and we got out, after applying tau to minus 1 over tau, a theta function of L star weighted by some L periodic function, just a different one. In fact, it is in effect the discrete Fourier the weight is in effect the discrete Fourier transform of the weight you started out with. So you started with a characteristic function, you wound up with a character. And so then, to keep track of the evolution of this theta function under composites of this map and this map, that is to say, under arbitrary elements of the full modular group, you are forced to keep track not only of this function, but of all of the rest of them. But once you have gone to this packet of 2 to the whatever theta functions, you always stay with the same packet applying some linear transformations. And in this particular case, it's easy enough to check because because the resulting modular group still has only 2 generators, you eventually find that this theta function, what did I call it here, theta of L plus W star, is modular, perhaps not for the full modular group, but for the congruent subgroup, gamma of 2, which is the set of all elements of the usual congruence group, which are congruent to the identity mod 2. And this happily is still generated by only 2 elements, t squared and its conjugate by S with no relations, and I leave it as an exercise to actually verify this. Okay, so that is our modularity situation for theta function of this kind. And in general, what you find is that it's going to be modular for some congruence group where the modulus will depend on how much you've had to scale the dual lattice to make it even. If you want to see one exposition of the general result, it's in Ivan Yetz's book that I've seen circulating here, chapter 9, and I'll outline a different approach in my 4th lecture if there's time. For now, I'll consider the following example, which is characterizing the Barnes-Wall lattice. And so that's the case where L is of rank 16, and the dual lattice mod L is Z mod 2 to the 8, which is what happens for the Barnes-Wall lattice, with the further constraint that, again, there is this extremality condition, with the further constraint that L and the scaled L star have no roots. Remember, these are even lattices, so roots have are just vectors of norm 2. And the claim is that if you use this together with the information coming from the roots, you have enough information to pin down the theta series of each one of the 256 cosets. And as it happens, that turns out to be enough to actually prove that your lattice has to be isomorphic with the Barnes-Wall lattice. So, I showed the theta series of such a lattice last time, right? So the theta series is equal to 1 plus 432q squared plus dot dot dot. And in general, we know that just as we do for the full modular group, the relevant set of modular forms for this group, for the group gamma of 2, right? So these are weight 8, half the dimension for gamma of 2. The space of modular forms is well known. Unfortunately, it's 5-dimensional. Fortunately, each one of these shifted theta functions, or theta functions of a coset, we have just enough information about to pin it down within this 5-dimensional space. So first of all, we know that under tau goes to tau plus 1, it gets multiplied by plus or minus 1. That cuts it down to a 3-dimensional or 2-dimensional subspace. And second, unless W star is in the 0 coset, in which case the theta function is just the theta function of L starred with a scaling. If W star is not 0, then we know that the theta function is big O of q squared because there are no vectors of norm, big O of q, because there are no vectors of norm q to the 1/2 and no vectors in that coset, no vectors of norm 1 in the scaled dual lattice, and no vectors of norm 0 in the coset. And what's more, we know what happens if you apply this tau goes to minus 1 over tau transformation. In that case, you do get a leading coefficient of 1, because you remember that you're now summing over all lattice vectors, with coefficient being plus or minus 1 according to some inner product, and here the inner product is 0. But left over is something which is O of, it's again O of q, but there is no vector of norm 1, so there is no q to the 1/2 coefficient. And so this gives you two conditions. There's this coefficient has to be 0, this coefficient has to be 0. Here you get at least one condition because you've already put it in a space where there is no, where the coefficients are only every other power of root q. And to make a long story short, these three conditions specify the form uniquely in either case. So, for example, if W star has norm, has integral as opposed to half integral norm, then you find that the theta series starts 32q plus some further terms, 122q squared, plus 2060q cubed, etc. But let's just look at this 32, because now we switch back from doing this complex analysis with space of modular forms and Poisson summation to thinking about the lattice geometrically. What is this 32 telling you? Well, it's telling you pretty much the same kind of thing that a count of 16 told us when we were studying E8. That is to say, we have a bunch of vectors, V in L plus W star. Well, remember the dual lattice, the quotient of the dual lattice by L has exponent 2, so whatever coset V is in, minus V is in the same coset, so there are 16 pairs, V minus V, and my claim is that any two of them have to be perpendicular, and the reason is that if I look at V minus V prime, for any two of these are actually vectors in L, and so these, remember, have norm 2. V plus or minus V prime is a vector of L which has norm at least 4, and the only way to have two vectors of norm 2 such their sum and difference have norm at least 4 is for them to be perpendicular. So that means that we have automatically found a set of 16 mutually orthogonal vectors in a coordinate frame with norm squared of 2, such that the difference between any two vectors is in the lattice. That is to say, we have found a copy of the lattice D16 scaled by 2 inside L, and because L is integral, that automatically means that the dual of that lattice is a sublattice of L, and so that immediately reduces to a finite problem of finding the correct the correct subspace, subgroup of this quotient, which will give rise to a lattice which has these integrality and integrality conditions and which has no roots, and that ultimately becomes a question in coding theory. And after spending some time studying codes of length 16, you eventually conclude using this that L has to be isomorphic to this Barnes-Wall lattice of dimension 16, and that also allows you to figure out again how big the automorphism group is, because to specify an automorphism, we had to take any of these W stars which are integral, but we know how many of them there are. Remember, the original theta function had a coefficient 4 and 320. We have divided them into 4320. We have divided them into sets, each one of which has 32 elements, and so that means that there are 135 of these cosets. And having done that, it follows that all of the cosets are equivalent, and so the number of automorphisms is basically 135 times the automorphism group of whichever code you have constructed here to make the Barnes-Wall lattice. Admittedly, if you know a bit more about the arithmetic of this lattice mod 2, you could have skipped the theta step, and the weighted theta step entirely, just started from the 4320 and from the fact that you get from computing locally mod 2 that there are 135 of these cosets, and that would force this number to be 32. So for many of these proofs, there are these two alternative approaches. That's true for the E8 proof I outlined yesterday. It's true for Conway's proof of the uniqueness of the Leech lattice, and there are several other such examples. Yeah? Come again? Oh, yes, thank you. It's always a cause of confusion with lattices that a lattice is contained in another lattice if its discriminant is bigger. And so because we tend to think about lattices in terms of their discriminants, we are tempted to put the inequality sign going the wrong way, and I'm afraid that I succumb to that temptation here. So thank you. Yeah, these inclusions are going the wrong way. We're going the wrong way. Thanks. Okay, so that's all for now for topic 1, which is weighted thetas. How much time do I have? How much time though?
20.
Okay, thanks. So that gives me some idea of where I am. Okay. Harmonic polynomials. Change of space entirely. Let P be the space of polynomials in n variables. So polynomials on Rn. And of course, it's a direct sum of polynomials of degree d, which I denote by this script p sub d. And I have this operator, the Laplacian, which is the sum over I of the second partial derivatives and is famously invariant under orthogonal transformations. And so it's the same regardless of what orthogonal coordinates I've used. And that takes each PD to PD minus 2. It turns out that the map is surjective, and the harmonic polynomials of degree d are the kernel of this map. So I denote them by PD upper 0, PD naught. Okay, here are 2 more operators. There is the Euler operator, which is the sum of x sub I d by dxi. If you like, it's the dot product of x with the gradient. That takes PD to itself, and it's called the Euler operator because Euler observed that, to use modern terminology, P sub d is the d eigenspace. This operator multiplies a homogeneous polynomial of degree d by d. And so we are looking for polynomials which are in the kernel of delta and in the d eigenspace of E. And let me put up one more operator, f, which is multiplication by the norm, and that takes PD to PD plus 2. So if you want to describe PD naught as an eigenspace inside PD, then PD naught is the 0 eigenspace of delta followed by f, which of course you can't see. Here it is. Okay, so why am I introducing E and especially F? Because they have these neat commutation relations. The commutator of delta with F is 4E plus 2N, N being the dimension. By the commutator of AB, I mean, in general, AB minus BA. The commutator of E with delta is, E with delta is minus 2 delta. The commutator of E with F is plus 2F. And this might look very familiar. That is to say, it will look like the Lie algebra for SL2. And in fact, this hints that you really want to look at E plus N over 2, not the Euler operator itself. And in fact, that says that delta E plus N over 2 and F span an algebra of differential operators that's isomorphic to the Lie algebra SL2. Specifically, if you like to have the usual notations x, h, and y for the basic generators with their commutation relations, you can take x to half delta, you can take h to minus e plus n over 2, and you can take y to minus f over 2. And once you have this, you can play all the games that you either did learn or will learn using the representation theory of SL2, using y and x as stepping operators that increase and decrease eigenvalues. And what you find is that the space of polynomials of degree d decomposes as a direct sum over, let's say, k running from 0 to d over 2 of the operator f, which you remember is just multiplying by the norm raised to the power k, applied to the space of harmonic polynomials of degree d minus 2k. So any polynomial of degree d that is any homogeneous polynomial of degree d can be written uniquely as a sum of a harmonic polynomial plus norm times some other harmonic polynomial of degree 2 less, plus the norm squared times harmonic polynomial of degree 4 less, and so forth until you run out of degrees because the degrees become negative. And the way you show this is basically this is the eigenvalue, the eigenspace decomposition of polynomials of degree d under this operator f delta, whose zero eigenspace is the k equals 0 summand. And it follows from this that any polynomial at all can be written uniquely as a sum of harmonic polynomials of some degree times powers of the norm. Anything else I want to say on this page? No. Okay, so having said that, maybe I should have said one more thing on this page, because I'm told that, well, John Hankey tells me that he will be doing some things with the Weyl representation, and I guess then I should say that these are all contained in the infinitesimal generators of the Weyl representation of sp2n. So there is an algebra where instead of these, well, okay, you have to you have to add 1/2 to these. You put in all of the mixed second partials, all the mixed polynomials of degree 2, and all of the xi d by dj's. That gives you infinitesimal generators of the Weyl representation, and this is the ON invariance in the Weyl representation. So the action of ON cuts out a little SL2. That's all that we need to develop harmonic polynomials. So, okay, here is P, and now that allows me to explain how we use weighted thetas, for which we're only allowed to use harmonic polynomials, to get at the notion of a T-design for which we have to use all polynomials as test functions. So recall that a finite set, let's say non-empty, in the unit sphere is said to be a T-design. That means that, well, for any polynomial of degree less than or equal t, the sum over the set, well, another way of saying this, the average over the set of P of V equals the average over the unit sphere of P. So that's what it means to be a spherical design. You can integrate any function of sufficiently small degree by just averaging over the set. And the claim is, because of what we have done so far, this is enough, it's enough to show that for all polynomials which are harmonic of degree less than or equal t, this condition holds. And the reason is, any of these polynomials can be written as, any of these polynomials, well, clearly that's a special case of that. So if you give me this, you give me that. The hard part is going back. And, well, if you give me any polynomial here, I can use this decomposition to write it as a finite sum of harmonic polynomials of degree at most t, multiplied by powers of the norm. But if you're just evaluating on the unit sphere, either here or here, then multiplying by a power of the norm is multiplying by 1. And so if you have done it for p, you have done it for any multiple of p by a power of the norm. So that is an equivalence. And what's more, the integral simplifies. Because, well, certainly if t equals 0, if d equals 0, then p is just a constant, and so the average will have to be, will just have to be the value, and that you don't even have to test. But because you can interpret the space of harmonic polynomials as eigenspaces for a self-dual operator on the sphere, they are orthonormal to each other. So if you take any polynomial of degree bigger than 0, it's orthogonal to the constant polynomial, and therefore its integral is 0. So that explains why. It's enough to check exactly the kind of polynomials that we are led to by the function equation for weighted theta functions. So, for example, supposing I give you some lattice L, which has dimension, so some lattice L, which is even, self-dual of rank n, which is 24m. Remember, that's the case in which we can have in some sense, the best hope for good sphere packing. And suppose then there is extremal, which means that a theta series of L has no unforced coefficient, has all coefficients 0 except the constant until you get to q to the m plus 1. In that case, if you look at theta LP, well, remember, you're taking, this is for a degree of p bigger than 0, then the constant term is going to vanish, and I'm going to get a polynomial, I'm going to get a modular form, also polynomial in E4 and E6, but a modular form of weight 12m plus d, which is O of q to the m plus 1. It vanishes to large order at infinity, at q equals 0. In this context, infinity is not minus 1 but 0. If you take tau to I infinity, then q becomes 0. At any rate, so there are no such forms except the 0 form, as long as d equals 2, 4, 6, 8, or 10, and also 14. This wonderful extra jump that we get for modular forms for the full modular group. There's this neat thing that you don't have any for weight 14. And once you have found that, of course, they also have to vanish if d is odd. I didn't put up odd d on the board because for d odd, values of p at v and minus v just cancel out. So, and if you look at the coefficients, each q to the m coefficient is the sum of this harmonic polynomial over all vectors of some norm, and that means that that sum is 0 for polynomials of degree, well, various degrees, including all degrees up from 1 to 11. And that means then that the shell of vectors of norm k is an 11 design for all k. So that's what we'll use for m equals 48 in one of our projects. And then there's an 11.5 design because you actually have that Svenkov's notation for what happens when you can also average spherical harmonics of degree 14. How much time do I have? 5 minutes, thank you. Okay, so I have to make some choices. I am on page 6 of my notes. No, I'm still on page 5. Page 6 is the last one. Briefly, if you want to get at equidistribution results, then you have a bunch of sets, and the idea of, and to say that they're equidistributed asymptotically as I goes to infinity, is to say that for all function f continuous on the unit sphere, well, whichever sphere, okay, there are finite sets on the unit sphere, the average over the ith set of the sum of f of v approaches the integral over the unit set of f. That's what you have to check for. That's what you have to check for the function to be equidistributed by uniform approximation, which is basically Stone-Warthus theorem. That's equivalent to check for all polynomials. And then by the same trick of expanding a polynomial as restricted to the unit sphere as a harmonic polynomial, it's enough to check for all harmonic polynomials P. So that means if you look at larger and larger shells of any lattice, not just one of these special extremal lattices, of any lattice, as long as the inner products are rational, you can translate the equidistribution condition to some condition on the growth of the coefficients of a certain modular form, well, various modular forms, one for each of these polynomials, but these modular forms are cusp forms. They still vanish at 0, at q equals 0, maybe not to very high order, but to some order. That's enough to make them cusp forms, and then cusp form estimates give it to you where at least for n bigger than or equal 5, and depending on how much more hypotheses you're willing to put on it, also for n equals 4 and 3. You can't expect to go further down. There's an example in my notes of the failure of equidistribution for the Gaussian lattice in Z2. But anyway, that's how theta functions are used to obtain equidistribution. And of course, you even have equidistribution in cosets using these weighted thetas. Once you know how to form weighted thetas by periodic functions and by harmonic functions, using both weightings at once gives you more results at no real further cost. Okay, I'm not going to be able to actually show how to construct the example of zonal spherical harmonics, but basically one way you can use this is to take, let's say you want to take some, again, we're back to giving yet, oh, thank you. We are back to giving yet another uniqueness proof for E8. Start from some even self-dual lattice, take a vector of norm 8, which is not a double lattice vector, then by Cauchy-Schwarz all the inner products are between -3 and 3, and they're integers, that is to say with the 240 minimal vectors. How many times does each one occur? Well, apply our rule to each one of our polynomials, which is v0.v raised to a power between 0 and 6. Here you get a 7 design, so you have just enough equations. Murphy's law is the statement that if you put in the equation coming from the next degree, which is 10, you don't actually get a contradiction. Well, here it's not Murphy because E8 is a beautiful thing and we want it to exist. Murphy is when you get the same kind of behavior for high lattices that you're trying to prove don't exist. At any rate, here you pay particular attention, as you usually do, to the extreme ones, which is n plus or minus 3. There are 8 of them, and either by pushing finite products around, or inner products around, or by playing some variation on this game of spherical designs, you can show that these 8 vectors all have the same inner product with each other. They're vectors of the same norm, which form a regular simplex in the 7-dimensional slice that you get by restricting them to the inner product 3 space. And then if you look at their differences, that means that they span the root lattice A7, and then you have in your lattice the direct sum of V0 with A7. That gives you a sublattice of index 8. There's a unique way of fitting it in that shows that the lattice is isomorphic to E8, and again gives you a way to determine its automorphism group. It's the number of classes which you got from the theta function multiplied by number of automorphisms of A8, which is twice 8 factorial divided by 2 because you have to make a choice in forming this lattice. And so I've silently omitted the factors of 2 here, or rather invisibly, not silently because I just told you about them, but I've invisibly omitted the factors of 2, and I have this formula for automorphism group of E8. So that's all for now, and I will finish at least 1 minute before time. Is that right? Just about. Okay, thank you.